Okay, today we're going to cover friction more in depth and the two kinds of friction that we can solve for with a simple model. Okay, and we're focusing our model on friction between dry solid surfaces. So let's start off with static friction. This is the type of friction that is going to change magnitude in other words, get larger and larger to prevent sliding or slipping. And it will reach a maximum value called the maximum static friction force. And then if that maximum is exceeded, then that object will start to slip or slide. And so you can see that in this series of images here, that first they're showing a box that has no sideways forces on it at all. It's just motionless. It's because it's got, because it's just got normal force canceling with gravity. But then something applies a leftward force here to it. And so let's say that's a rope. It's trying to pull it to the left, but that force is being matched by a force of static friction. And so therefore it remains motionless. It stays where it is. Then somebody pulls harder with a greater magnitude force to the left. But there's still friction between this surface, whatever it is, and the box. And Fs grows larger. So still the box remains in place. Finally, we reach an even larger force to the left. Let's say that's tension again. And then static friction still grows to match that. Okay, and again, it's drawn up here, but it's taking place down at the surface between the box and the outside world, the surface. If it's the floor, we're talking about maybe a wooden floor. Okay, so that's preventing that object from accelerating. So in this case, it seems like, okay, well, that's preventing motion. But actually, static friction also helps things move, which seems counterintuitive. But this set of diagrams is showing that when you're walking, you are relying on this force, okay? Because when you put your front foot down, okay, your front foot was in motion, and then you put it down on the ground, and the friction is going to stop that foot, okay? And then you are gonna push off, okay, of that foot. You push down and back when you make a step. And then Newton's third law says that the floor is gonna push forward on you, okay, and up a little bit. So when it does that, that force, which is really friction and normal force, okay, is providing the force that propels you forward. And that relies upon the fact that your foot does not slip, that your shoe is going to stick to the floor. So without static friction, if everything was frictionless, that would also be bad, because we couldn't move without these forces that we rely on through Newton's third law to move forward. Okay. Then we have a type of friction we call kinetic friction. So when two surfaces, dry surfaces, are in contact with each other and are sliding or slipping relative to each other, then we call that kinetic friction. And the differences here are that this force of friction, if you compare it to the force of static friction between those same two surfaces, it will always be less than the magnitude of the maximum static frictional force. And it's not going to change. It's just going to be a constant value for any two surfaces and an object on a surface. Okay, so how this works is, going back to the very first example, if we got this box finally to move, so we have a force large enough to win, okay, over the maximum static friction force, then the box starts to accelerate, and then it's moving, okay? And now the kinetic friction force is in charge. And that will be a smaller magnitude, and you can see it on this graph. So then suddenly the force of friction drops in size. Still pointing opposite of motion. And then you will see it's weaker, okay, and it's not changing. Okay. From the AP sheet, the model we're using, which is a simplified, model of how to calculate the size of these forces. It just gives you one equation, okay, for the force of friction. You'll see these absolute value signs around the forces because the direction is going to be based off of your free body diagram, like the situation, which way is it going to slide, or which way is the applied force pulling or pushing, and then which way would it slip or slide if it could. Then friction would point the other way, okay? And so you're going to see this inequality here, and really that applies in the case of static friction, which means it's less than or equal to mu s, is like our slipperiness or stickiness factor. The bigger the mu, the stickier the two surfaces are to each other, okay? And then also this depends on the normal force between the two surfaces. And then if it's a kinetic force of friction, then it's not an inequality. It is an equal sign here. And then that's a different mu value, okay, for those two surfaces, and it's always less than the static mu value. So scientists have studied all different kinds of surfaces, and every time a new solid surface would be invented or something, I suppose you could go do an experiment and find out what the mu value is for that surface when it rubs on another one, okay? So when we talk about solving friction problems, I have a couple of examples for you to watch. But the key questions to ask yourself are, is this object, or when we get to rotating wheels, okay, is it slipping or sliding? If the answer is no, then static friction applies, okay? So then the tactics are, you can look at the free body diagram and use some other forces on the free body diagram to solve for the force of friction, okay? Don't just blindly always use this formula, because what if the force of friction is not at its maximum? Okay, like look at dude right here. He's not even pushing the couch. Okay, what is the force of friction? 0. Okay, so don't just plug stuff in here. That will be a trick question sometimes. So if there's no applied force, dude's not pushing the couch, applied force is 0, static friction 0, it's just not even applicable, okay? Versus here, maybe, is it about to slide? Okay, then that's like a clue where it's like it's at its maximum value. It's like about to go. then you can use this equation, but be very careful. Then if it is slipping and sliding, then you're going to use kinetic friction formula. And again, sometimes you know how hard he's pushing. So then okay, is he pushing at a constant velocity then? Do you know the acceleration? You know, we have our tricks from the last chapter, and then we have our new equations.